Yeah, so good afternoon everyone. We are starting with our session, which is session 14, Evolving Trends in Utility Automation. The session partner for this is Center for Development of Advanced Computing, which is C-DAC. It's a premier R&D organization of Ministry of Electronics and Information Technology. So, this giving a small session background, this session will examine the evolving trends in utility automation in collaboration with Center of Development of Advanced Computing (C-DAC) and National Mission on Power Electronics Technology, who are working towards a forward-looking approach to enhance energy efficiency, reliability, and sustainability of utility services through advanced technologies. So, for this session, first of all, I would request Ms. Tripta Thakur, who is Director General NPTI, to please come on stage as she is chairing the session for this evolving trends. Welcome, ma'am. Now I request Mr. Faruk Kazi, who is the ISGF Chairperson and Dean Studies, VJTI Institute. I welcome you, sir, on stage. Thank you. Now I request Mr. Renji Chacko, who is Senior Director and Chief Investigator, NaMPET, C-DAC, to please come on stage. Thank you, sir. Welcome. Now I request Mr. Abby Joseph, who is Scientist Director, C-DAC, to please come on stage, sir. Thank you. Then we have Om Krishnan Singh, sir, who is Scientist, Ministry of Electronics and Information Technology. Welcome, sir. Then we have with us GURUNATH, sir, who is Associate Professor, IISc Bangalore. Welcome, sir. We also have with us Ritesh Keshri, sir, who is C-DAC Wireless Charging. Welcome, sir. We also have with us Vishwajeet Singh, sir, who is Director, ANZ, India and APAC, AutoGrid. I welcome you all. And I think we can first start with Tripta ma'am. I request ma'am to please give a welcome address and we can then start with our session. Thank you, ma'am.
Thank you. Welcome everyone for this session, which is before lunch. So we all are very energetic, although this session is a little late. But we are going to talk in a very important session, 14, that is evolving trends in utility automation. We all know that we are in the era of energy transition, where the important pillar for the energy transition is digitalization. So we are in the process of digitalization, and in this digitalization, we are going to discuss different trends which are happening in India as well as abroad, which are really going to help the utility to gain efficiency. And the smart grid is one of the very important discussion point. Today, we are going to discuss about the smart grid technology in this session, and then the new technology in the form of AI, ML, which are going to penetrate the power sector in a massive way. Then when we are going for digitalization, there is cyber security is a very, very important aspect where we really would like to make our system cyber resilient. So in today's discussion, we are going to discuss about the cyber security measures to make our utility cyber resilient. Then we all know that everyone is going for energy security concern and for environmental concern for more and more renewable energy in the grid. So the integration of renewable energy, which is although very challenging also because there is a lot of system integration issues which we need to solve when we are having 50%, which is India is aiming by 2030 to have 500 gigawatt renewable energy in the grid. Then another technology which is IoT and sensors, which are really going to help us for monitoring and control of power sector. Then, of course, when these new things are coming up, we really need to talk about the regulatory aspect and policy support. So that is also one of the important segment for today's session. And then what are the different challenges when we are moving for this energy transition era for utility automation. Then what way we can collaborate with the C-DAC and NaMPET for getting more support from them for implementing this automation into the utility. So I'm very sure that this session is going to be brainstorming session which is going to give us a new ideas for the new technology which are really going to help us for automation and going to help us to move further for energy transition era. So welcome all of you for this session. Thank you.
Thank you, ma'am, for an enriching welcome address. And now I request Faruk Kazi sir as the moderator of the session to please start with the session. And I request, we have presentations from, I think, each one of you. So we can limit this to like 10 minutes, 10, 12 minutes. Then maybe we would like to have this an enriching and engaging engagement. So we can click that for like 10 minutes max. Okay, thank you.
Yeah. So first of all, thank you, Tripta ma'am, for the excellent opening remarks, because that has now set the tone for the rest of the panel discussion. So I also would like to thank ISGF for actually bringing in the experts in all those domains which work on the automation sector, as well as C-DAC, which has always remained at the forefront of the technology development. So I would be first calling upon Shri Renji Chacko sir, Senior Director and Chief Investigator of NaMPET C-DAC, to share his views on the evolving trends in utility automation. Thank you.
Good afternoon, very good afternoon to all who are assembled here. Myself from Center for Advanced Computing, C-DAC Trivandrum in Power Electronics Department. We used to do a basic R&D organization under the Ministry of Electronics, and we do basic application-oriented activities in power electronics and power system solutions in various sectors in association with academic institutions as well as industries and startups. So we have a consortium of research and development team, including academics, and we lead as an application-oriented R&D team, as well as with industry and startup associations. We have about 14 centers. I will take this opportunity to little bit tell about the mission program, that is National Mission on Power Electronics Technology by the Ministry of Electronics, as well as our activity C-DAC. And our colleagues will explain more on the automation, on the utility automation activities as the thematic area. So when thankful to the ISGF forum to give this platform to give an overview of our activities. When we heard about this IGF, in fact, it is the first time we are associated with ISGF in a good way. So when we heard about this workshop, we initially thought of associating as a demonstrating technology demonstration as in the exhibitions, but later during we had a good discussion with our Sri Renji and team, and then we also had the programs like in the National Mission program. We had activities like awareness creation programs across the sectors, the activities going on. What are the technologies available, what is the possibility of indigenous technology development that can be given to industries, etc. So then later on we have came up with an active participation with in the form of a session partner, and then in this program, and later on in the future we will be looking for a bigger way of collaboration with the IGSF for the better outreach activity of the technology R&D activity that is happening in various forms. So the C-DAC Trivandrum Center is acting at the nodal center for the National Mission on Power Electronics Technology, And the power electronics group itself is about 100 technology members, technical members in various sectors. And we are working in major activity in this power system and power electronics area is the National Mission Power Electronics Technology, which is a community led by the C-DAC Trivandrum Office of Power Electronics Group. We work on different sectors like a New Horizon in Power Electronics Technology with the association of academic institutions, premier academic institutions including IISc, IITs, NITs and even some of other organizations. And we also work with advanced technology. In this program, we work in advanced research development and deployment activities, and whatever technology developed, that also is taking into the field deployment and find whatever the possible solution that can be directly taken to the industries. And also we do a lot of awareness creation program like short-term programs and workshops, and this association will be fruitful. So here mostly we are hearing about the real technology deployments in the field and the problem that we're facing. And here we just want to announce that there is a lot of technology R&D activities are happening, and there are community available for the solutions that can be given to industries and startups on for the Indian conditions, or when we go for maybe it will be okay to go with whatever technology available as far as the cost factor is concerned and the immediate deployment activities are concerned. We can go with whatever technology, whether it is imported or whatever way. But when we go for the higher penetration into the market, and when we look for a sustainable technology implementations, we need to have a basic R&D with us. We need to go along with these deployments. We need to work with local R&D activities and technology developments. That is what we provide under the National Mission Program NaMPET. And the thematic areas are smart grid solutions, new power electronics devices like gallium nitride and silicon carbide devices activities, real-time simulation and offline as well as real-time simulations for the power electronics and power systems. In e-mobility sector, we have a lot of activities that drives or in charging solutions and other power system, the impact on the power system for when we come, the large quantity of the charges come into the field. So those kind of analysis being happened. On power quality, we have a lot of applications like static power compensations or battery energy storage systems and harmonics compensation, etc. So we have a lot of technology transfer activities happening with ministries, user agencies and startups and academic institutions. So that is what it is. A forum is available. This will be able to address a lot of challenges that is happening in the deployments by industries and startups. The New Horizon activity, actually the thematic area is on the new generation of power electronics with wideband gap devices, which will provide more reliability, system integration and miniaturization activity. Actually, in the power system, in this domain, we are going with the frequency of operation of one order higher, the high power converters about maybe 100 kilowatts of order, maybe working right now with the 10 kilohertz or operation maybe, with this WBG devices will be operating at much higher frequencies of 100 kilowatts or 500 kilowatts that way, which will reduce the size and the reliability. That way it will be more integration can be done in the system level, and high frequency operations and related technologies like planar magnetics and other the sensor devices that is required for the high frequency and high voltage applications in power electronics like MEMS systems, MEMS sensors. These are being addressed in this one. Mostly these kind of activities are being addressed by the academic institutions. A consortium of academic institutions are first time happening in this development area in the R&D field. Multiple academic institutions, including multiple IITs, are working together for a single solution, which many solutions are being happening in this one. So also basic exploratory research projects are happening with individual academic institutions also. In deployment of technologies and which are already developed. This NaMPET program is already there in the 10, 15 years, almost 20 years now, now it is happening. It is in the third phase, one of the most successful development activities in the ministry. The overall ministry activities from the Ministry of Electronics and Information Technology, Dr. Krishan Singh is there. He will be explaining on what are the policies, what are the initiatives that is happening at the ministry level. And the NaMPET is one of the most successful development R&D activity that is initiated by the Ministry of Electronics. In the deployment field, we had microgrid for different villages, remote villages and tribal villages, especially many, almost about a dozen installations from the 10 kilowatt to 1000 kilowatt level of deployments are available, and also some of the technologies are being taken by, or customization has been done by the industries also. And in the green energy system for community buildings, we have net zero solutions, low voltage DC powering and smart metering technologies, which are in the deployment with association with user agencies, the electricity boards and other industry partners. And also we had activities in the wide area monitoring along with the phaser measurement units, and for monitoring of this will provide a lot of solutions in the utility automation as a whole. In the application-oriented activity, mostly we are, as of now, concentrated on e-mobility, smart grid, and high-voltage power electronics. In the e-mobility, technologies for charging solutions and drives applications, especially with wide bandgap devices, silicon carbide as well as GaN devices. And the test platforms like battery emulators, which will provide solutions for the technology developers, academic institutions, otherwise, as well as with the R&D organizations which are doing activity in this field. The smart grid solutions are mostly on power quality management, renewable energy and storage integration into the distribution sector mostly, and advanced metering infrastructure solutions and digital substation activities are happening. And our colleague Abhi Joseph will be explaining more on this technology in details. We also have higher voltage applications, especially in voltage levels of more than 10 kilovolts, even the 100 kilovolts of level for the medical applications like X-ray power supplies, pulse electric field for food processing, etc. As a whole, the program as a whole is happening with project modes, different projects in the different category we mentioned about in the New Horizon. About 17 sub-projects are happening in the application-oriented, mostly with leadership from C-DAC Trivandrum. About 16 sub-projects are running in this field, and deployments, about 5 sub-projects are deployed in the different fields with industries and user agencies. And the foreign NaMPET can afford what it can afford as a whole. The technology that has been developed with the support of industries and ministries, it can, the NaMPET can offer different technologies in this associated field. It can be product technologies, it can be directly taken by the industry for manufacturing, as well as customization solutions and the technologies in smart grid implementations where the technology support will be given. And we provide technology hand-holding for user agencies and industry startups, etc. for a long-term the technical support hand-holding. In fact, in one of the solutions that is being gone into the Indian Railways for about 7 years as of now for the three-phase loco propulsion applications that we are providing almost 10 years of technology hand-holding from this forum. And also we are providing, we are taking care of the technology outreach and awareness activities, which will provide more technology related information and more training activities which are required for at various forums, maybe at startups, maybe at the customers and other agencies where more training on the latest technologies of the power electronics is concerned. These have been, this kind of support and technology are being offered by from the NaMPET forum. These are the various products and technologies we have developed in recent as well as in the past, which are being offered to industries, startups, and also being implemented in the the turnkey implementation basis with the various, in association with the technology partners and user agencies. We have a demonstration stall, it is available there, and some of these technologies have been demonstrated there. Our TOT partners solution also been there, so we can have a detailed discussion on what is the scope of association that we can with various industries and agencies. Just a use case that I will like to just give an example of how these developments are happening. One use case is the energy efficient low voltage DC powering for the example is in houseboat applications, where these houseboats are very common in the Kerala backwaters, which are being powered for a very inefficient way with second hand the automotive engines, and also a lot of powering is using the gensets which are polluting in the environment. So we provided a rooftop solar. The system is having an aesthetic look like the houses in the boats, which we will be able to utilize for a night stay, etc. in the backwater. So in that one, a rooftop flexible solar panel has been provided, and most of these the systems on board are being powered directly from the DC supplies at 48 volt. So low voltage applications like the lights, fans, and also even the air conditioners are operating, and in the refrigeration systems are all required solely mostly on the DC supply, that is mostly on brushless DC based the systems are being used in the fans and in the refrigerations, etc. And so this provides a very efficient way of integrating solar into this kind of system. So this problem statement has come from the Energy Management Center EMC Kerala, which are looking at the energy efficiency and other things in the state of Kerala. So they have provided such a problem, and we have discussed with other agencies like National Institute of Technology Calicut, which is having energy auditing and energy efficiency kind of the research area, which provided some kind of the simulation or some studies which provided some definitions for what all the system requirements, etc. So we provided a customization solution for this one, and some local industries are associated with implementing this one in a houseboat system. So these have been operating very successfully without the reliability is extremely high because it is locally operating at 48 volt DC. So how this extension, this implementation has taken forward by the government of Kerala is that the right side that the picture you are showing is the 5-story building that is Kerala Strategic and Corporation, which is like Niti Aayog in the local state. So this building as a 5-story building is completely operating with rooftop solar and 48 volt DC supplies on all systems, and some of the system may be operating at AC also with the conversions. We have connection with the grid also. So this kind of extensions are happening, and we also are working with other institutions and academics, etc. We have about 5-10 installations already in this one, so 48 volt direct. And maybe in most of we are working with the BIS standard for having a standard for hybrid power distribution scheme using for any houses or any apartments, etc. We can have a 230 volt supply as well as with a 48 DC supply we can operate efficiently. So this kind of the consortium mode of activities are happening. We have a platform for such kind of problem solution. We are looking forward for such kind of problem statement in smart grid technologies also to take it forward, and also looking for collaborations with the stakeholders in this field for further collaboration and solutions. So thank you very much for the opportunity, and our colleagues will explain more on the technology front for this. Thank you very much.
Yeah, so thank you, Renji sir, for introducing to us various tech development that is happening in the C-DAC, particularly in the domain of power electronics and the automation. So I request audience to park their question for some time. We will take them at appropriate stage. So I would like to now invite Shri Om Krishan Singh ji, who is Deputy Director in the Ministry of Electronics and Information Technology, to share his views on the evolving trends in utility automation.
Thank you very much. Good afternoon to all of you, respected chairman, distinguished speakers on dais, experts of dais. Yeah. So myself, Krishan Singh, I'm a Joint Director in Ministry of Electronics and IT. Actually, I look after area, power electronics, electric vehicle subsystem development, and electronics related to agriculture technology. So this is the framework, structure of the ministry in which C-DAC is one of the partner, autonomous society, which looks after basically this power related activity. One of them is the NaMPET as discussed by Sri Renji Chacko. So as we know, earlier in 2005, basically conventional technologies were being used in the area of power electronics for converting the electrical energy into the another form. So at that time, ministry has taken an initiative, mission mode program, National Mission on Power Electronics Technology in 2005 with some 10 to 15 institutions. At that time, we have set up the infrastructures, all the tools and related infrastructure has been provided to them so that they could enable to the industry whatever the requirement. So in 2005, in the basic infrastructure, we have taken up to the research level, and further in the second phase, that is started in 2012 to 2018, we have developed numerous technology which has been deployed at different places. So in the first and second phase, whatever the technology related, like as mentioned, ISUW vehicle control unit for Indian Railway and all, it has been developed, deployed and field trial across the country, 2 lakhs kilometers in all the weather and terrain. And then currently more than 1,000 locomotives is running on that technology. So it has been a successful program. So based on that, the next program, that is, the next phase, third phase, is started in 2019, especially in the different category, focusing to the renewable energy, microgrid, and traction, including e-mobility also, LVDC aspects. So in this, basically, along with the blue sky research and development, deployment, as well as we have taken care of the application-oriented approach. Not only in earlier phases, it has been found that the gap between the academia and industry hand-holding. So in the third phase, we have taken care about that. This is specification and other hand-holding and collaboration with the industry partners, users, with the different ministry. So in all these 3 phases, so far we have developed, as mentioned, many technology which has been commercialized. More than 15 technology we have developed in this, and it has been commercialized through the 23 industry. So these are the some industry partners which has been collaborated under this program, and these are the academic partners which has been part while developing the technology. So as I mentioned, there are like various applications in defense, in space, in locomotives, in renewable energy. It has been developed and deployed. So in totality, we can say, like from the clean room, from the device aspect, GAN-based device, we have developed the product up to the field. So all the technology what we have taken up under this program, it is under the mandate of the government of India, where we have to move, because we all know that currently the energy, 95% of the energy being converted from one form to the another form. So this is very much required, this power electronics aspect right now. Under the e-mobility aspect also, while taking care, we have developed different kind of the charging infrastructure, chargers we have developed. Not only we have taken silicon based, especially when we go for the form factors and the efficiency aspect. So we have taken care of the WBG based devices also in the different verticals and different sectors. So these are the some chargers that we have developed, and it is some of them has certified also, and it is commercialized through the different industry. So these are the some, roadmap where we are moving, starting from 2005, and now we are moving to in different mission mode differently. We are going to make a different mission mode program catering to the different application of space, renewable energy, as well as locomotives. So we are targeting that. In parallel, green mobility, government is focusing like introduction of this 500 gigawatt by 2030. So to cater, along with the renewable energy integration and all, we have focused the e-mobility aspect, where we are targeting to develop the electric vehicle subsystem, including the different components. As you know that currently most of the components, more than 90% of motor, controller, converters, chargers is being imported from outside. So to localize, to indigenize the things, this initiative has been taken up. And in the consortium approach we have taken up, where the designer will be there, like academic partners and R&D institutions will be there, and then manufacturing partners who could manufacture that component, and the end user who is going to use into their vehicle. So with this consortium, government is supporting to develop these kind of components also. Currently, it is under, some development is going on. So if you talk about the Ministry of Electronics and IT, right from the design and development till the manufacturing, the supports is being provided. Not only, you can see research development like NaMPET, EVSS program we have provided. For testing and certification, MIT has a different society, Samir and all, where the testing and certification, EMI, EMC of what the components we develop, it is being provided. For manufacturing, there was a MCIPS scheme. Now this is the SPECS scheme, where this kind of critical component, electronic component like motors and these converters, it being supported for manufacturing. 25% of capex is being provided. For the, all the ecosystem, whatever needed right from the design to up to the commercialization, it is being supported by the Ministry of Electronics and IT. So some of them, this is the output. Some of them has been commercialized, motor, controller, developed by the different institutions and agency. So these are the roadmap that we are targeting towards achieve the indigenization of the components of the electric vehicle also, along with the different ministry like DHI and DST is also working on that. So MIT is also working with them and try to meet the target of the government of India, like 30% introduction by 2030. So we are moving towards that. So these are the, currently in the EVSS program, we are working, earlier we have worked some 4 or 5 components. It has been commercialized. Currently it is 14 development is going on in the consortium approach, which is under process. And not only the government is supported, now this time, currently industry is coming forward, not only in the kind supports, they are giving the funds to take the TRL, 5 to 6 to 9. Generally, it has been found in the earlier phases of the NaMPET and in the EVSS also. Private, industry is reluctant to support from the beginning, but now industry is coming forward to support, and in the especially in the innovation and R&D part. So this is the good sign, and we also hope through such kind of forums our documents, reports should come out, so that how the different ministry who is working with the different agencies, different associations, different industry, so that a meaningful, whatever the target of the government of India, we can meet in a time-bounded manner. So as in the last session, one speaker, telling about whatever the technology, what we are importing, it is not as per the our, it is very relevant. What the things we are importing that have been designed, developed as per their road condition, their traffic condition, their environment. So we have to take up the initiatives as per our conditions, because we are, from 5 to 10 degrees Celsius to we go up to the 50 degrees Celsius. So the challenges in the design of the controllers, converters, everything, it is very crucial in that sense. In the power electronics, EVSS, this is apart from this, because this in this session like automation, so one in utility, that is smart meter activity. Smart meter, we have developed a single phase and three phase as per our requirement. In indigenous smart meter we have developed, and now we have transferred that technology to more than 14 industry. So not only that, as per the, the standards is also very crucial aspect mentioned by previous speakers. So we are trying to incorporate our standards so that it would go to the IEC level. So this is, support, what we are targeting to meet. But I request this ISGF forum to come out with the, otherwise what happens, generally we have seen, we go in the different forums, such kind of the conferences, everything happens, but what is the outcome of this, how we will go ahead, that action part is remaining, and their follow-up. So I request some documents, some reports come out as a result of that, and then how we will move forward. So this is, mighty prospect. So we look forward that a good collaborative R&D indigenization of various technology in smart grid technology, green technology. So which is also the mandate, and make in India and make for the world. So thank you very much for giving this opportunity.
Thank you, sir, for sharing the vision of ministry and also sharing the success stories that we had so far in indigenous technology development. I would now like to call upon Shri Abhay Joseph Ji, Scientist Ji, Senior Director, C-DAC Trivandrum. We will take questions after this session, so if you have any questions, you can just write it down.
So, good afternoon, dignitaries on and off the dais, my dear colleagues. So, I'll go a bit into details of what we have done at C-DAC under the ambit of NaMPET, especially in the area of smart grid and automation. So I'll just show you some of the case studies, some of the technology that we have developed, some of the technology that has gone to field, and some of them already has gone to industry for commercialization also. So basically, one of our thematic area of NaMPET, as my previous speakers indicated, it is in renewable energy. So in renewable energy, we have been working extensively. In fact, we have indigenized the power conditioning systems, the overall indigenization of the power conditioning system for say kilowatt to megawatt scale solar PV power plants, wind electric generators, and hybrid power plants where you have multiple renewable energy sources and battery interfaced. Then actually the thing is that we have been working with our own design, overall design. The power electronic converters are designed by us and engineered by us also. So we interact with industries to come out with a kind of products which are in TRL level up to say 9, and we go to field with the support of different user agencies. We have been working along with West Bengal Renewable Energy Agency, working along with Kerala State Electricity Board, Energy Management Center, MNRE agencies. These are some of the activities. And then another key area where we have been working is microgrids. We have many number of microgrid installations. I will come to some of the system that we have already been implemented in one of my later slides actually. So another important area where we have been working is in power quality. Power quality we have been working in STATCOMs basically. STATCOMs means reactive power compensation and active filters for harmonic compensation. We have worked on UPQC, Unified Power Quality Controller. We have developed DVRs. We have worked on actually power quality devices for different applications, that is custom power solutions. We have developed D-STATCOMs, which are basically integrated in distribution grids for power quality mitigation. And another area of expertise that C-DAC can share is on the state-of-the-art digital controllers. We have our own controllers. We make our own controllers with the state-of-the-art processors, and all the control software are being developed at C-DAC. So a total indigenization of different technologies that has been happening, and then field deployment also. So actually all these technologies, once it is verified or demonstrated and evaluated in the field, we keep it open for industries to take the technology. So we have many technology partners with us. They take up the technology, do the incremental engineering and go for productization. So in fact, in the smart grid domain, so I would like to specifically mention about a project which has been taken up in the NaMPET. So that project is Smart Power Quality Center. In this particular project, we are trying to address different aspects of smart grid technology for distribution grid through some 6 sub-projects actually. So we are working on digital substation, development of digital substation architecture. We are working on advanced metering infrastructure that my previous speaker has mentioned. One of the major area where we have worked is in smart meter development. C-DAC has already indigenized the technology of smart meters, and we have transferred these technologies to around 14 industries in the country, and some of them already have commercialized it also actually. So we are as a next stage we are working on advanced metering infrastructure, and then another is intelligent sensor network for distribution grid actually for monitoring the distribution grid. We are trying to build an intelligent sensor network for a distribution grid. Then utility scale bus system, that is the power electronics and other control aspects required for battery energy storage. I will come to that in a later stage slide. Then power quality, distributed power quality resources for the utility grid. Then solid state transformers and solid state switch, which are a bit futuristic technology. We are working on that also. The attraction of these projects are actually we are tying up with Kerala State Electricity Board. They have shared one of their substation and some of the area under the substation to integrate all these systems and make a realistic system for demonstration. So in the case of DSS, actually these are the development that has been taken up. Actually we have built our own substation merging unit. Then we have built our own smart digital IO module, bay control unit, and SCADA dashboard also. Indigenization has been done, and now we are in the process of integrating all these things in an actual substation basically. So what we are trying to do is a redundant system we are trying to build so that we can both the digital substation architecture as well as the conventional legacy substation, they are working together basically. Now smart meters, so you can see the photographs of 3-phase and single-phase smart meters that has been developed at C-DAC. And as a next stage, smart meters alone may not work. Actually, we have to go for AMI. So the head-end system and DCU, those things are also being totally indigenized. We have developed that, and we have a head-end software right now. It's not that extensive as that is in the market presently, but what we have done is, as I mentioned, the utility is working in close collaboration with us, that is Kerala State Electricity Board. They have given us some use cases, subset of applications. And this particular software, it is Smart Electrical Energy Measurement and Analysis, SEMA. This particular software is capable of catering to those requirements. Presently, we have a small section of the distribution grid where we have integrated all our smart meters, and they are communicating to this particular red-end system. And electricity board's tariff evaluation is being done on an experimental basis. So this is the status of that particular project. And then another is intelligent sensor network. Again, it's an ongoing activity. See, a few years back, we have worked on this phaser measurement unit, synchronized phaser measurement unit. We have developed this phaser measurement unit for transmission grid, and we have implemented a kind of a wide area monitoring system for a 220 kV network of Kerala State Electricity Boards with say 10 numbers of PMUs, and we had developed some of the wide area monitoring applications also. So with that kind of experience, and with the support of Professor GURUNATH also will be mentioning about it, I suppose. With his support, actually, we have moved on to micro PMU technology now, which can be used in the distribution domain. So that activity is also happening right now. And then another area where we are working is on the transformer monitoring system for the asset manager, which also we consider as one of the important equipment or important technology that should be integrated in the distribution domain for asset monitoring and protection. Another area, actually, it is bus battery energy storage system. So in all these projects, our focus mostly on the power electronic system. So we are trying to indigenize the power electronic system along with the other auxiliary technology required for the realization of the overall system. So here what we are doing, again, this is going to field. We are implementing it in one of the substations of KSEB. And here what we are trying to do is, we have three types of battery. One is lithium ion, and another is flow battery, and then lead acid battery, or different capacities basically. So we are building power hardware or power converter hardware or interface hardware for lithium ion, sodium sulfur, flow battery, and advanced lead acid battery. And we are building BMS system for working along with the grid integrated operation actually. So that is what is done here. So on the left hand side top, you can see how it is integrated. So there is a PCU, that is power conditioning unit, plus BMS for the integration of the battery. And on the right hand side, one of the typical power converter configuration we have shown there. So there is a multi-level inverter directly connected to grid, and we have isolated DC-DC converter on the left hand side, you can see, which basically are used for connecting batteries. And you have a connecting transformer also. So this kind of a scheme is being built there. So on the bottom side, you can see some of the power conditioning system that we have developed already. In the laboratory level, we have tested all those things, and now the field implementation is happening. And soon, maybe in another 6 months' time, we'll be ready with the technology. Then another area, see, power quality devices. We have been working extensively, maybe for the last 2 decades, in fact. We developed STATCOMs, that is a reactive power compensation system, which can cater dynamically varying or fluctuating reactive current. So we developed it as a custom power device. We have integrated it in some of the industries for compensating the reactive as well as harmonic currents. Now we have different versions of the STATCOMs that can be integrated on a consumer level, which can be integrated on a network level. And even we have recently developed this STATCOM that can be with a packaging suitable for outdoor deployment. It can be integrated in a transformer yard, basically. You can integrate that. So then actually we have worked on STATCOM technology which is capable of compensating the power factor or reactive power requirements of wind electric generator also. We actually integrated in a 500 kVA 500 kilowatt wind electric machine, and we have trialed that. That technology is also presently ready with C-DAC actually. Another area is DVR. DVR and unified power quality controllers. The power hardware and control are already developed, tested, and technology is ready for transfer actually. Now in microgrids, it's a major area where we have been working. We have developed different types of microgrid. We have the off-grid microgrid, on-grid microgrid, means microgrid that can work in the on-grid mode also. So we have modular redundant hardwares which is capable of working along with the multiple resources, can be wind or solar or even biomass. Then even we integrate DG sets for backup power. Then there is a battery bank. So this, see, we started with the silicon. Now presently we have, seen all these technologies, we started with silicon IGBTs. So considering the power density requirements, we have migrated to silicon carbides also, silicon carbide technology also. So the whatever power conditioning system that you are seeing on the bottom side is basically built with silicon carbide. So you can see one of our installation in a forest station, which is basically a container based installation. We have multiple microgrid installation, totally indigenous, deployed in say tribal hamlets basically as the. Now again in last day when DST was presenting about microgrids, we were also fortunate to get associated in that project, actually in the Indo-UK consortium project. Our thematic area in that one was to build reliable power conditioning systems for microgrid, which can work in harsh environmental conditions, in saline, humid environment. So accordingly, we package the power conditioning systems, and we have one installation in Lakshadweep presently, so which we developed along with IIT Bombay. And in fact, in microgrid projects, we are getting support of IIT Kanpur also. As my Sri Renji Chacko mentioned, almost all these projects, basically it's running in a consortium mode. We have academic partners either as a project partner or as a consultant or technology consultant. In that way they are associating, industries associating, user agencies also closely associating. So this is one of the system that we have developed. So then another important work that we are presently, interesting work that we are doing is interconnection of microgrids, that is interconnected microgrid. It is for a tribal settlement. Idea is we are trying to interconnect the microgrid so as to exchange the resources. So there is an AC interconnection as well as DC interconnection that we have made there. So that work is in the ongoing, it's an ongoing activity basically. So that is regarding microgrid. Now, some of the off-grid solutions also we have developed. In fact, in the DST's off-grid activity, we have built a vaccine refrigeration system. The power electronics as well as the refrigeration technology required for the vaccine refrigeration system was totally, it was built, and we trialed it with along with Sri Chitra Institute of Medical Science. They have a community medicine department. With that, we have taken this system for vaccination drives in tribal hamlets, remote tribal hamlets. Now, I would like to request my colleague, Mr. Udayasagar, Actually, he's one of the key member who is working in e-mobility technology, that is especially in the charger part. So I just request him to support me by explaining this charger part with a couple of slides.
Good afternoon, everyone. So we are also into the development of EV chargers. So basically, we have developed the AC as well as DC chargers. All are SiC and GaN based, they're just WPG based devices. So for AC chargers, there are two. Through 3-port single phase AC chargers and single port AC chargers. These are of 3.3 kilowatt power levels, and we have also developed SPV chargers which is of 3.3 kilowatt, and it's a bidirectional. When the vehicle is connected, it will be the vehicle power will be fed from the solar, and when there is no vehicle, the power will be fed back to the grid. That is the idea behind that SPV charger. And coming to AC fast chargers, we have developed a single phase 7 kilowatt and 3 phase 22 kilowatt AC chargers. And coming to the DC chargers, 15 kilowatt, which is of GB-BART standards, and 50 kilowatt for CCS as well as CHAdeMO standards. So also in e-mobility, we have developed integrated drive systems for EV vehicles. So one 30 kilowatt PMSM drive, which is of liquid cooled, and this is also with SiC devices, SiC MOSFET devices, and we have also attempted and successfully we have developed it with the active gate driver, where we can achieve zero current and zero voltage switching. And now we are planning it to integrate inside the motor itself, and we are redesigning the PCBs. And coming to the 3 kilowatt GaN based BLDC drive, we have also successfully completed a 3 kilowatt GaN based, that is a 48 volt output drive. And now we are modifying the PCB in a circular form so that which can be attached into the frame of the motor itself. So again, coming to the e-mobility technology V2X, that is vehicle to grid as well as business to home. So this here we are developing 20 kilowatt V2 vehicle to grid and 3.3 kilowatt vehicle to home. The vehicle to home idea is to take the energy stored in the battery to the vehicle for essentials loads like or in case if you are in a remote area, we can take the energy stored in the vehicle to local loads or for critical loads if required. So also the communications part, that is CUI, is also developed to meet the requirements. In vehicle to business, during peak hours, the energy stored in the vehicle can be fed back to the grid, and during non-peak hours, we can use the charging, use the vehicle for charging. So these two are of bidirectional capabilities. And also we are into onboard charger developments. That is also GaN based, and this we are developing in joint with IISc Bangalore. That's a 3.3 kilowatt, and in future we may be coming up with the 6.6 kilowatt and 22 kilowatt modules. So here it is fully, almost it's like a 98% efficient system, and in the front end is a totem pole PFC, and the rear end, that is the secondary side, it's a dual active bridge, which is also capable of bidirectional power flow, and its power density is greater than 40 watts per inch cube, and now we are trying to increase the power density by packaging. It's a completely IP65 grade onboard charger. So that's it from the e-mobility side. Thank you.
Thank you. Thank you, Uday. So thank you very much. So I think if you have questions, we can take up during the discussion session. Thank you very much.
So Thank you, sir, for sharing amazing work that you are doing. So probably this is the right time to take a couple of questions, and I'll take undue advantage of being moderator. So one question that many of you may also be having is, and any one of three speakers can answer to this, that if somebody wants to approach to you for transfer of technology, then can you briefly tell us what can be the process or the way in which they can approach to you?
So basically, we have the technology informations are available on C-DAC website as well as on the MIT website. Some information also we have under the NaMPET. If you Google it, NaMPET is there is a website, and also we have social media platforms in the YouTube, other things technology available. And then probably on most of the technologies available for transfer will be available, and contacts, other things. So the requirement is that wherever it is required, just basic information and the further details of the, even in some of the technologies are ready, the modalities are ready. And maybe some of the things where customization requirements may be case to case basis, we have to find the modality of the operation. So that way informations are available and contacts are available. Even you can contact with a few of us. Then we will probably, what we will do is once the requirements are known, then we'll have some kind of an agreement between us, and which will tell what is the technical and financial modalities required for the transfer, as well as the long-term technical support that will be required at this. So in that agreement it will be done, and during that process the complete technology transfer. If it's a product technology transfer, the complete the documents, bill of material, training, everything will be done through that one. If it is a customization requirements, it will may take a little more time to do the customization. That will be detailed in that process. So this way, if it is a product technology which is available, it can be done quite in a couple of months or so. And if it is customization, it may take up maybe 6 months or 12 months. But we will provide long-term technical support also. That can be done. So it will be mostly the technologies are for non-exclusive basis to any industries. That's the way to do it. Thank you.
Yeah, so thank you, sir. Thank you very much. We can take one or two questions from audience if you have, before we can move on to the next speaker.
I have a question from Joseph C. You have mentioned that you have a interconnected microgrid. So is there any limitation, or what is your range for interconnecting microgrids?
So in this particular activity, we have AC as well as DC interconnection. So DC interconnection we are attempting because you can connect asynchronously to AC sources using that. But then there is a limitation, the distance between the two microgrids. And the limitation is what voltage that you have to, at what voltage you have to interconnect, because the drops will be more. AC interconnection we have done multiple times, there is not much problem in that. But in the DC interconnection, this becomes a bigger problem. So in this particular work, actually we have association with IIT Kanpur, and for the particular case, we have done our kind of studies and identified the voltage level at which we have to interconnect, most optimal value, and then actually the protection systems also. Like that only we have taken up that work actually.
Thank you, sir. I now invite Dr. GURUNATH GURRALA, sir, Associate Professor, IISc Bangalore.
Good afternoon, everyone. I think we are close into the lunch. So, my name is GURUNATH GURRALA. I'm a faculty from Electrical Engineering Department, Indian Institute of Science. So, just one thing I want all of you to notice that the technologies that have been demonstrated are not lab prototypes, okay? They're all field, deployed, tested. And one thing we also have to understand that the capabilities that we have today are enormous capabilities, and that's what I want to bring in. So this is from the R&D side, from the academic institutions, as well as the industries together and the R&D institutions. I want to find out from the utility side what really they need when they really want to do any automation. So let me take a small layman's approach. I'm a layman and I don't want to know what is going on in electrical utility, let's say. So what I know about electricity, and then what I know about communication. If you look at all the things, we will be talking most about the communication and the IT infrastructure, which is essentially the component of the automation, right? And then how do I exchange the information in a better way? So when I want to till date, I just wanted to look at what's happened to the energy as well as to the communications, right? So what changed and what not changed, right? So let's look at, I think I'm just dividing it in 0 to 10, 10 to 20, this is my age, and most of you are at the same age and maybe slightly younger. So don't just look at the pictures, look at the intent behind these pictures. So you can see all these things. I remember all of you might have seen even in your early days, right? And that's basically what is the physical systems which are using electricity. I've just brought them. There are many things which have changed, but this is something which I definitely know that I have used electricity for these. Light, motor, fan, trains, maybe the electric heaters, refrigerators, and then the electric cars with batteries, right? Today we are seeing the big things. But one thing is that there are very few, okay? I mean, very few homes have them. Unfortunately, I mean, I don't have them at home, and I've seen a lot of these, right? But on the other side, on the information side, if you just look at these, you have newspapers, you have Morse machines, you have radios, telephones, and the physical letters, and then you have the television, right? These are the news that we have. Many houses doesn't have it, right? And I know that all these are actually supplied by only 2-3 things. One is there is a utility wire that comes to my home, and I have a plug point where I plug in. If nothing is there, I'm going to go for battery. And I'm sure even in the future 10 years, the past 10 years, you will be talking about these 3 things. That how do you get energy to your home? How do you tap it to your devices? And if that is not there from your home, what are you going to do? That's basically storage, right? After 10 years, there was a small change that I have seen that the volume has actually increased, the costs have come down. That means the people's ability to purchase has gone. Not much of innovations, frankly speaking. So anything that drives low cost is only the demand, not many a times it's the innovation. And you see the bottom side, these are also increased from few to many, okay? That's what has happened. And one small thing got introduced, what we can say is some kind of an internet at those days, I know. And then we come to 25, then we started looking at, because we are overutilizing the energy, and then now looking at the energy efficiency has come, but nothing has changed, okay? The stars have come on all appliances. And then the bottom side, you have seen many other things, like you have telephones, you have internet, color TVs, and all that stuff, right? But everything that is being powered is those 3 only, okay? Nothing has changed, right? Then star rated has gone to different levels, and you have seen pictures are same, but they have transformed into those conditions. But they're still their functionalities, everything remain the same. They are being powered by the same. Bottom, you can notice that there are changes have come, that many have become few, and many things have even extinct, okay? Right? But still, you need these 3 for all of them. And the last, current generation, none of the bottom has actually sustained. Everything is gone. Only thing remained is whatever you have in your hand, okay? And the top still, we have to use them, right? That's basically today's requirement. And you can't forget that requirement. And to power these, you need to have these 3, okay? Those 3. And that's what actually we need in this life. Okay? Do you agree with me or not? Right? Correct. So, what are we talking about today? These 2, which could sustain change in different forms and came to a single option today. And literally, there's no way I can communicate if I lose my phone, except asking my friend, give me your phone. But earlier, I have a lot of options to even communicate to my home. Unfortunately, we don't even have landlines at home. So that's the scenario today. And you see at the top that remained the same. If you tell me if something has changed, I think it has changed in superficially, but not the fundamental things. That's what is technology, okay? Something that can stay and feed the lives of the people is what is the most important technology that we have to look for, not driven by the business, okay? Right, so let me I could live all without any of these today we are having. I could communicate without electricity, although I have very few options and very few people have. I mean, I have many options, very few people have, although they are slow. One thing that I can say, I have fresh air, I have beautiful sun, and I never had to worry about how I will go out on the roads because of the scorching heat. I never had to think about during my life, but today I'm thinking about it. So I could still live without all these even today, very frankly speaking, but we have very short lifespan of all these things, and these are all use and throw. I mean, I can't do anything with any of these things. I cannot communicate without electricity. Many people cannot live without phones, right? So what we are trying to do now, we're trying to capture and use things which are naturally fresh and available to us, which are helping us to sustain. Anyway, that's we can't change. So now, what is not changed here for a long time, the plug, the socket, the battery, the wire, and the pole, I think that's what his utility is all about, right? He has to only deal with this. Does it have to deal anything with that? So then what are you talking about? You're talking about Ohm's law and Kirchhoff's law, which never change in the life. They have to remain. And that's what we wanted to change on the name of what is called as automations. So let's look at. So I would say that these four, what I'm talking about, the bare minimum things which is needed for the utility are like hardened steel. You can't change them, right? If you really want to change those things, then you need to have a furnace to actually molten that, right? So the question that you need to ask is something that has not changed at all for the years, something that is revolutionary and cannot stay for more than a few years. Am I going to change it? And we have to be very careful in answering this question, because this is actually linked to the billions of lives of the country. Don't just get behind from the countries which don't have manpower, okay? The countries which have manpower has to think about this very well. So what you are trying to do? Information, communication, and you want to have every hand. Let us make it as a furnace on the name of automation and try to change this as like a molten metal, right? So this is essentially what is automation that today people are talking about, and I want to see whether this can be achieved. Right? I don't have an answer. I'm a old school electrical engineer, and I know that there is no answer for this, right? So, but let's think about what is needed. Generation very well known to everyone because it is not directly interacting with the people. Transmission is something that it's well taken care. Automation very well known. What is today is basically that customers can actually directly pay for it, is where we are going ahead and trying to see whether we can do something. That's what discoms. But we have to understand that discoms are not as well equipped with money as the other two top that you have seen, right? This is the fundamental problem. So automation, if you talk about, first thing that we wanted to do is make sure that generation and load are completely balanced, and we tried to make a lot of electrical processes to be automated as much as possible. The first level of automation happened at invention of the breakers and the relays, which can actually do all that stuff. Then we wanted to go to the next level because the manpower is so high and the security was not really good, and we went to the next level of automation layer, which basically all your numerical relays and all that stuff. But still, we are not happy that we wanted to make more profits, and we are investing on the reducing the manpower cost to actually go for the remote things, right? So that's what. But this automation has a caveat, right? We are now getting into a realm of cyber security, and we don't have answers for that today, right? So we are also doing a lot of other automation. So today, on the name of power system automation, what we have is that we have increased the power system profits and security a lot, but today we don't know whether that profits can be go away just because of one thing called cybersecurity, right? So this basically the status. So now let's look at the characteristics of our Indian utilities. Density of their service areas are actually much larger than any advanced country that you actually look at. They directly affect the livelihoods of masses because the densities are more. Directly influenced by the politics, and we should not ignore that. Haunting non-technical losses and starving balance sheets. These are the technical characteristics of these. Whether you like it or not, this is the problem. Now, if you really want to bring automation, what is that we need to do? You can't just say businesses are coming, they have 100 years old technologies or 30 years old technologies. Tell me any automation company today that offers you EMS system has been built just in the last 5 years. These are all built 30 years back, and they are just doing old wine in the new bottle and selling to us, and we are saying that we are automating it. Don't you think we don't have the capability to do these automation by ourselves in the country? Let's ask ourselves. See the technologies that you have seen. These are the latest technology we could build and prove to the world. Can't we do the technologies that we have been established tens of years ahead? Can't we build ourselves? So all that is needed is that understand the need of the utilities, that they can't afford these money because it's a huge investment. What can be done? I think we need, today's energy society requires these things. Yes, you have seen, we are good at it. Smart everywhere. But this requires a lot of other things. You need a lot of computational power. You need a lot of software thing to be developed. But this software should not ignore the domain knowledge of the people, right? Domain is most important. So you need to have a blend of people. People coming from this domain, sit together, this is the only thing that I can do. And you take the domain from the other people and say, hey, what you want to do for us? We have a great establishment, right? We have actually done the UPI system, which is actually revolutionary in the world. Billions of people are being fed through this. So we have established the ability to build softwares which are proven for billions of people. So why do we actually still knock out the doors of outsiders and say that give me the utility automation software for me, right? So that's basically the question I want to do. See, many utilities need helping hand. From what? Use the technology and the capabilities that we have. Build a stack like UPI for the utilities. That's more than enough. So that's what I wanted to call today to all of you, that the challenges that the automation brings is domain challenges, of course, will always there. Out of domain challenges, of course, that has to be addressed. But I can't address through an electrical engineer. His job is to keep the lights on 24/7, right? So with that, we also get several layers of challenges, security, reskilling of the manpower, and all that stuff. And do you think that the utility has that bandwidth to do all that stuff? That's where the academic institutions, R&D institutions have to come forward to see, can I support this guy with the helping hand, right? So what is needed? These are the software architecture. So my call is to say, indigenous utility stack can we actually build and give it to the utilities, right? And we have the capabilities and we can do it, right? Can the mighty actually help us? Can the C-DACs, CPRIs, academic institutions come forward and say that a UPS stack like stack can we actually build for the utilities to help them to navigate through it? So this is the call. Okay, did I do anything? I tried to make my hands a little bit dirty, and I'm completely a simulation guy, but I have done with C-DAC support that we have made our hands dirty. What is needed? We have to look at monitoring. Monitoring requires you to get some devices. Can we build? I can show you that all the examples that they have seen are being built, right? Analytics and optimization. I'm sure we have enough capacity in this country. Agile teaming, which essentially means that you need the middleware software, which essentially talks to different devices and can build it. There's a company called Kalki Tech, the first of the company which has actually built a lot of protocol converters, and it has sold and shown to the world that it can do that, right? So assistive services, right? You have dashboarding and all that stuff. We don't have dearth of knowledge. That's all it is needed for the best stack to be developed, and we have all the capabilities. So we just need the stack which needs to be developed for the utilities. Of course, this can feed all the poor countries and the countries that are advancing in the world, just a stack. right? And we have the capabilities. And of course, we built an open PMU on a hardware. We built some open source software stacks at IISc in collaboration with people. And all that looks like is this. You have a layer at the bottom, which actually interacts with different devices, a layer in the middle, which makes sure that your applications interacts. And this is any generic stack, and we have so many great companies in India, which has actually developed so many things, right? So this is a interface which I have built. I don't say it's a great thing, but I can say that we can build things for our utilities by ourselves. Cyber security features are something is a concern today. We can't depend on the outside. We need to build ourselves and make sure that this is mine and I know what the vulnerabilities it has. Let's wake up and build for ourselves. This one device we built, micro PMU, everything built by us except the chips because I can't help it. And we also built some energy infrastructure labs where we want to make our students who make their hands dirty understand that this requires a lot of engineering brain. So we built a lab where we have generation capabilities, where we emulate different kinds of generators. We have transmission capabilities. We built same as a substation as it is in the lab. Please come and visit us. You will see whatever outside existing, you will see inside, same operations. So all automation things can be tested inside your lab. This is our transmission systems. We also build real-time digital simulators because this is more important when you are having so many controls have to interact, whether the software or the hardware can work together. And we built an indigenous simulator thanks to the person who is here. And it's just 10 lakhs. And everything is open sourced and we built it. And this can be actually utilized across the utilities just like that, right? And we also embarked our journey towards the cybersecurity, looking at the aspects by ourselves, and we are trying to build people across the country to come together and build something for the country. So with the visionary of Mr. Keshri, the former director, CMD of PowerGrid, so we have started this center. So that's all. So my comment is that let's wake up and synergize our capabilities, look at the ecosystem from our requirement, not from the outside business pressures and trillion-dollar economy. Okay, thank you very much.
Thank you, sir. Thank you very much for a very interesting perspective on the evolution of automation. And your passionate call indeed resonates with all of us. So now I request Shri Ritesh Keshri ji, C-DAC wireless charging, to give his thoughts on this topic.
Good afternoon. I'm Dr. Ritesh Keshri from BNIT Nagpur. I'm an associate professor in electrical engineering department, and we are working for wireless charging with the support of MIT, and we worked together with C-DAC Thiruvananthapuram and some of the industry partners who basically have supported technically, such as High-Rise Transformer Nagpur and Bose Research Private Limited Bangalore. So let me go ahead. So basically, because I'm an academician, so I try to go in that way, like Professor GURRALA explained. That was a really very nice. When we talk about battery charging, so we have to understand what actually it is. So while we say that we are charging a battery, it means that we are trying to push the current into the battery by some circuital arrangement, external circuital arrangement, and so we get the battery charged. Then another terms comes what actually is a fast charging. So to understand fast charging, we have to see that generally batteries are sized or specified in terms of either ampere hour or we get kilowatt hour. So suppose that a battery is there and having a 100 ampere hour capacity and terminal voltage is 48, so it will be a 4.8 kilowatt hour battery pack. So if even though kilowatt hour is given to us, we have to just divide it by nominal voltage, and we will be getting the ampere hour capacity. And let's say a battery is having 100 Ah capability, and we are discharging it with a 20 ampere per hour, then our battery is going to last theoretically for 5 hours. But if we discharge the battery with 10 ampere, then the battery is going to last for the 10 hours. And similarly, if we are charging the battery with 10 ampere, then it will get charged in theoretically 10 hours. So this 10 ampere discharge, for this case 100 Ah battery pack, is called normal charging, and this we defined as C by 10. So when we say about the fast charging, or better say faster charging, then for this particular battery, which is 10 ampere is nominal, normal charging, if we give 20 ampere, or 30 ampere, or 40 ampere, or 100 ampere charging, so accordingly the charging time is going to get decided from 5 hours to 10 hours to 1 hour, like this. So these factors 2, 3, 4, 5, 6, 10, these are called degree of fastness, that how fast we are going to charge our battery. So this is basically a faster charging definition. And then what are the different ways of charging? We can charge the battery in a static way or in a dynamic way. So when both the charging point and the battery are stationary, then we say it is a static charging. And if either of them are moving, then we say that it is a dynamic charging. So static charging can be a conductive charging. You can see on the top one, this is one of the typical case of a charger in which we have a PFC rectifier, then buck converter, and then finally we are having a battery pack. And then second case below, you see that on the right side, that is a schematic of a wireless charger in which we have a coil buried into the ground and which receives energy from the grid, which could be 230 volt or 415 volt supply, means single phase or three phase. And then another coil is at the base of the vehicle, and there energy received by that coil to the vehicle, and then finally it is modulated, means conditioned to submit the energy into the battery pack. So this is a case of a wireless charging. So what are the different technologies basically we say which comes into the wireless power transfer, because wireless charging is a case for that one. So basically two types of wireless charging we can say that. One is called near field wireless power transfer, in which can be near field means it will be a short distance, maybe few centimeter to some meters, and it can be capacitive and inductive. And how we identify it? In case of capacitive wireless power transfer, electric field is going to dominate, and basically two metal plates will be there, and whatever the capacitance across this one is there, that is utilized to transfer the energy from transmitting end to receiving end. And inductive wireless power transfer, magnetic field is stronger, and in this case that coupling is done to the inductors. And then next is far field wireless power transfer. Definitely in this we need to go to the radiative zone, whereas in case of near field we work in the non-radiative zone, and which is quite safer for us. And this near field wireless chargers are quite popular at present, and people are exploring the cases of far field wireless power transmission. Then other, like we can define static charging, then quasi-dynamic and dynamic charging. In static, both the coil and the transmitting coil and the vehicle are stationary. But in case of quasi-dynamic charging, vehicle moves slowly over the coils. I will show you one of the case for that one. And in dynamic charging, vehicle does not slow it, rather it moves with the same speed and get the energy. And like here you see that one diagram I have shown you, in which magnetic field and electric field both are appearing together. So we have to understand this one, because we have studied in our class 12 also. When both the electric field and magnetic field is available in our system, they start traveling. So this is useful for the wireless power transfer. So we never see that we have only inductive or capacitive transfer, rather we have inductive resonant coupling. Like this is this type of work we do. But this is also dangerous for us if we don't work with this proper arrangement, electromagnetic field transfer, then we may damage our devices. So we face lots of challenge while working with this wireless charger. So basically they create EMI problems also. So we need to handle properly. This is an example of capacitive wireless transfer. Then you can see that coupling is done to the two parallel plate capacitors, and that inductor is provided to make it resonant coupling, so that the field can travel to a farther distance. Then this is the wireless charger. That same schematic what I have shown you before, that in this we receive energy from, it could be single phase or three phase. Then we have a power factor correction rectification, and then high frequency H bridge is there. And if you see here that the coil, what we are seeing, the two coils are separated in air, so they have the mutual inductance, but that mutual inductance is very poor, very less you can say in magnitude. So we have a relationship X equal to omega m, and omega is 2 pi f, means frequency function. So that's why we have to increase the frequency of transmission here, which we generally keep at 85 to 90 kilohertz, and so it gives us a much better coupling. And so this is the reason that why we work with 85 to 90 kilohertz here. We generally don't go beyond this one, because if we go beyond that, then we will go into the radiative zone because of the because if you see the injection of the current, what it is there in the H bridge is only from the H bridge to the coil is square wave. So for, fundamental component is there, third harmonic, fifth, seventh, up till this is okay. But if we go beyond that one, it goes into the radiative zone. So that is not allowed. So that's why this particular frequency is kept. Even though we don't modulate the switches here, if you are going to modulate, even within 85 to 90 kilohertz, we will have the frequency component which will fall in the radiative zone. Okay, and then we need compensation, because we have to overcome the issue of the inductance, which is affecting the injection of the current into the system. And once we receive the energy on the receiving side, again we do some compensation, and then we have a rectification, high frequency, and then a buck converter is there, which is not necessary always. If the charger is vehicle dedicated, not required. But it is, if the charger is not vehicle dedicated, means any of the vehicle is coming over it and getting charged, then this buck converter is required. Otherwise it is not required. And this is also required for the safety of the battery, onboard battery, because no one will receive, can receive anything what it can be, a charger is trying to push into the vehicle. Then these are the cases what we have developed at VNIT. On the top one, on the base, you see that we have a transmitting coil, and the power electronics part is also there. And on the base of the vehicle, you see here that we have a receiving coil, and rest of the power electronics is inside. And below it is a charging platform over which a vehicle gets there and get aligned and get charged. And these are like, why basically we are trying to explore this wireless power transfer, because we don't want that we should care more about the charging the vehicle, rather we should care about the autonomous mobility. Like we just have to be autonomous everywhere. So we don't need to think like whether battery is charged or not charged. So wherever the vehicle is getting opportunity, it will automatically charge, whether it is stationary or whether it is in motion. So three possible cases, like you see here, in fact four, we have shown you that now the case is that we are talking about the one vehicle, one charger. So it is something like the cost of the charging arrangement could be very, very high, and it is not possible to afford for every service provider. So the concept of us, automated scheduled fast charging could be quite better. So we are working on this also. And so we will be having only one central charger, and that is going to schedule the injection of the current into the different vehicles, whether it could be conductive or it could be a wireless one. So this is also going to improve the battery life. But at the same time, the same central charger will be able to facilitate multiple vehicles to get charged within the time spent, depending upon, suppose that one vehicle owner is that he wants to go just out in 1 hour. Another wants to go out after 4 hours, and next 10 hours. So this charger can automatically adjust by itself with the informations and provide the sufficient charge within that span of time. Then second one, you see that it's a representation of right side top one. That's a representation of a dynamic charging, which it could be a quasi charging also, what I explained to you. And then third case we have developed at VNIT. And so that this is basically a vehicle-to-vehicle connector. Suppose that you are having a vehicle and I am also a vehicle, and we want to exchange the energy for a short duration, maybe like 10 kilometers of charge, so then we can do it. It could be both conductive as well as wireless. Okay. And then for fourth case, you see that we talk about the agricultural drones, where farmers, like if you see the current age drone, you have to keep the multiple batteries. So one discharge replace another battery. So you have to take care of the charging process. But those drones can also be autonomous by the mean of this wireless charging. So we are, with some company, we are also trying this case of charging. Okay, this is the case what we have developed at present. This is a 1.5 kilowatt 48 volt wireless charger, right side one, and this second one is 5 kilowatt wireless charger. And first one that at 48 volt, it can charge a 4.8 kilowatt hour battery pack in 3 hours, whereas the second one 5 kilowatt is kept for made for four-wheelers, and that can charge that four-wheeler in 7 hours, you can say, like this. And below that you see that efficiency plots we have done. These plots are for the very first version of the charger. This 1.5 kilowatt charger. So we were able to achieve up to 17.5 centimeter.
Sir, can you please conclude, because
yes. Okay, thank you. So just I concluded. So efficiencies, etc. You can see that we are getting around 81% well-to-wheel, means grid point to battery efficiency. That's a good. And for closer distance, even we are getting more than 90%. Then different types of coils arrangements are there. Some are for stationary and some are for dynamic charging. Then like here I saw that we need to make ferrite cores, etc. arrangements, so that more flux can pass through the receiving coil, so that we can receive higher energy. Then misalignment arrangement is very, very important. If we don't do proper, then we will fail to transfer the power. Then topologies are there. We cannot say that only inductive is there, because I explained resonant is there. So different topologies, series, and parallel series, parallel arrangements are there. They have different impact on the power transfer and safety of the power electronics also. And then shielding is always necessary. If we don't do shielding, then we are going to harm the person who is sitting with the vehicle. So generally specified limit is 75 microtesla within the coil, and beyond that with the churches it should be even less than the tube lights. So I am happy to say you that what we are getting is only 19 microtesla, and even tube lights which are there at our home, they emit more than that. So our development is completely safe. This is the first prototype what we have made, 576 watts, and this was from the funding of MIT. When actually in past I received a young faculty research fellowship from MIT. So we have used whole of that money to develop this first prototype of wireless charger. So on the success of this one, we get another funding from the MIT to do this. Then these are some results. Like here I have tried to show like at each step what is the efficiency we get, and the last one result what you see here, that is with the misalignment of that. And so we were successful to making it 50%, up to 50% of the misalignment. And these are coil fabrications, layouting, and thermal evaluations what we have carried out. So this is, and recently we have initiated transfer of technology for this wireless charger to C-DAC Trivandrum. C-DAC Trivandrum we have handed over, and then Bellrise Pune has is taking this technology, so that is already initiated.
Thank you, sir. Thank you. So I'm sure we have a lot to talk about this, but we had some 30 minutes spillover from the previous session, and we cannot keep waiting too much before we go for the lunch. So we have a last speaker, so I don't want to take question at this point of time. Let's hear first the last speaker, and then we'll see how much time we get and how much energy we have before we opt for the lunch. But these questions can always be taken during the lunch as we move ahead. So I now invite Mr. Vishwajeet Singh, Senior Manager APAC from AutoGrid.
Good afternoon, everyone. I'm Vishwajeet Singh. I represent Uplight. We were earlier AutoGrid, but we got acquired by Applied. We provide energy management solution based on artificial intelligence and machine learning to utilities across US, Europe, Australia, and also in India. We have run demand response programs with Tata Power in Mumbai and TPDDL in Delhi. So they are basically using our software systems for this, for their program. So in view of time, I'll keep it short and try to make it sweet as well. So basically, if I take a step back, and I'm basically focusing on the challenges which utility face, and then we as a solution provider, what do we, how do we solve that problem? So if we look at what is happening in this utility, especially in the energy domain, there is a transition or there's a shift which is happening from a centralized generation, regulated utility, monopoly in the market, to a more decentralized generation with a lot of variable renewable energy resource penetration. And then, as we call it, prosumer, a new category of customers is emerging, which is not just a taker from the grid, but also giving it back to the grid. Be it your customers who have rooftop solar PVs, who have EV chargers, who can give it back to the grid in case of V2G use cases. So what is needed is that the utilities, as of now, they are running still with legacy SCADA systems, right? And in order to solve this problem where you have issues in the grid not at a very high level, but also at a localized level. So how do you solve those problems when you have a DER penetration, distributed energy resource penetration? And also there are concerns from the control room, from the grid operator. How do they manage these issues at a local level? So what happens and what is being tried now, and it is being understood that how do we bring the grid control room to the prosumer? Basically, how does the grid operator sitting in its control room has a visibility right down to the level of end consumers, you and I. So people like us who have smart ACs, Wi-Fi enabled ACs, smart meters, in coming times EV chargers and EV systems, rooftop solar inverters. So how does utility gets a visibility, situational awareness of these DER? And then looking at that DERs, how do they solve their own problem? So there is a problem, but there is also an opportunity to solve that problem. So if I look at this entire framework, and maybe it's still early days, especially in India, because the penetration of DERs is still low. But in next 5 to 6 years, when we expect, for example, 30 gigawatt of EV load to be there in the system, or be it 10 million rooftop solars to be deployed by the central government scheme. So those problems are going to come. But then how are other markets, other utility markets, they're solving these problems? So if I look at it, there are problems at the grid level. So what the grid operator is facing, he has these DERs which exist today in terms of wind, solar, storage, smart homes. But what they need is that they need to manage the grid in a way which is automatically restored. It's self-healing. And then how do they optimize the overall system so that the resiliency and the grid stability is achieved? So what they need is that they need system which can actually look at the localized level. Basically, for example, a system which is connected around a distribution transformer. How do they look at those constraints? How do they predict what is going to happen right now, maybe in next few minutes, to the horizon of next few days? So how do they get that situational awareness? And this is where new energy management solutions are there, which are being used, which allows these utilities to forecast in a more effective way. Of course, network level forecasting is a challenge in itself, but if you look at different ways of forecasting, there are ways to tune those machine learning models based on site data to get an effective result. So how do you forecast the system? How do you get the access to the end consumer devices? And then how can they manage the constraint by controlling the end assets? So it's a grid level problem which the operator is facing, that they need a situational awareness. They need to manage the constraint. They need to manage the constraint not by purchasing more power or by installing a new substation or upgrading the transformer, but within the consumers, how can they use those DERs in order to solve those problems? Then at the edge level, which is the level at we consumers connect to. For example, a smart meter, right? A smart meter is fetching the energy consumption data from our home. Or maybe an EV charger, which is connecting to a EV system and then giving it back to the grid. The sensor-based systems which are monitoring your devices. So, and inverters in case of rooftop solar. So at the edge level where this computation is happening, we need a system, we need, and other markets are looking at these. How do we have a visibility down to the level of these individual devices? So till now, utility had the visibility up to the distribution transformer, right? Or maybe a smart meter consumption data. But what is happening down at the individual consumer level hasn't been known or is not visible to them. So this is where we need systems, systems which can actually stay at the grid level, at the edge level. And what they would do is that through APIs, through open standards, they're able to connect and communicate with our devices. So what it helps what it provides or the outcome is that, be it a smart meter, by analyzing the smart meter data, this edge system would be able to provide you the insight of how the consumer is, the energy consumption pattern. What is the charging and discharging pattern of an EVSE charger? When it can be, can you shift the charging load to evening, or can you discharge the vehicle in the night when it is not being used? So those are the things, those are the flexibility, those are the times when these DERs can be utilized. And this is what grid edge-based systems, software systems do that. So they have the visibility, and they also calculate the flexibility available across these devices. And then the consumer level. So I think in this entire energy transition, you and I, the consumer level, the consumer are the main, at the core. Because if you're trying to engage with the end consumer devices, the end consumer needs to be part of a utility program. It needs to be engaged and continuously, given insights of how their consumption pattern looks like, right? So the need is that you may have heard about many of these utilities having billing management systems, right? They have some apps or a website where consumers go and pay their bill. Much beyond that, if you have customer-facing applications where you can actually interact with the consumer, like, look, this is what you're consuming, this is what you can shed, this is what your bill savings. I think the more you engage with them, the higher the participation will be from the consumer side. So this is a threefold problem where you're looking at the grid level, edge level, and consumer level. And there are systems which can solve this problem, which can address at these various levels. So as I mentioned, that bringing the control room to the prosumer is what the new utility segment are trying to do across different markets. And then at the grid level, what is needed? So basically an end-to-end solution which is looking at optimizing the grid, such as we connect all the stakeholders, as I mentioned, the utility itself, the consumer itself, and then how do you optimize the supply and demand at every level? So you need to optimize your supply and demand even at the local distribution level, because with this intermittency of the renewables, with this proliferation of DERs, the demand and supply management is a much bigger challenge for the utilities. It's a real-time problem rather than being a planning decision. And then there are tools which support these kind of issues. They can solve these problems, where the utility needs to think about how do they incorporate DER penetration into integrated resource planning. How do you do network level forecasting? How do you generate your network hosting maps? Basically what it means is that, can you predict how much of DER can be connected to the grid? How much is the capacity at a particular substation level? Can you connect another solar PV? Can you connect another battery? So what is the network capacity? What connection, install connection limit you can grant to a customer? So those kind of insights are generated. And then of course, the situational awareness in terms of visualization, dashboarding is a core element of it. Looking at the consumer behavior, can you ask your end consumer to shift their load? Can you nudge them? Can you encourage them to do so? So that comes under demand response. And of course, with the new breed of DERs in terms of EV and EV fleets, can you manage it? Can you optimize it in a way that the EV charging load is shifted to the time when the grid is not is in an off-peak period? can you ask the EV fleet owners to contribute to the grid by providing grid services? Of course, it's not just related to software systems, but it's also related to how do utility generate these programs and how do they develop a business model for everyone. And of course, there's also a way to monetize the additional flexibility from our assets. They can also go, the utilities or maybe aggregators can participate in trading in markets. And there are other energy markets where they have allowed DERs in the form of VPP to participate in the market. And in the last, I would just touch upon what is this entire ecosystem of IT-OT integration looks like. On the consumer side, it's us, residential consumers with thermostats, air conditioners, all kinds of load, the commercial consumers with smart buildings, HVAC loads, etc. And then all these evolving landscape of DERs. And then on the other hand is our conventional SCADA systems from the utility. So we need to bridge this gap. We need to bridge this gap between the energy companies and the customers, so that the energy utilities are able to have a view of what's happening on the behind the meter side, and then they're able to optimize it better in a way that the grid operation or the grid resiliency is achieved in a better way, rather than upgrading your network, rather than procuring additional power. So what we need is that integrated system approach. You integrate the transmission and distribution ADMS systems, the customer billing and settlement systems, the trading desk as well. And then on the other end, on the customer side, we have customer engagement portal. So there is a continuous engagement between the two stakeholders, such that it's a win-win situation for everyone in this equation. All right, I think I'll skip these slides, but I would just like to touch upon 2 points very broadly. With all these controllers which we were talking about, EV chargers, inverters, software systems, I think cybersecurity is at the core. So what we need is a layered security with infrastructure and boundary defense. The utility need to comply with highest of standards. The data needs to be encrypted, whether it's in rest and transit. And cybersecurity is not a support functions for utility, but it needs to be a part of their strategy. So overall, there are a lot of things which utility can look into in terms of how do you limit the access to these systems based on the role, based on the utility side, who's operating these systems. You abide by international standards. There are a lot of frameworks which are there which ensures that how you manage these systems in a much more secured way. So work needs to be done on that front, and that needs to be taken up if we are talking about grid modernization and smart grid. And last but not the least, on the policy side, I think from the RDSS scheme, there have been a lot of interventions in the form of 8.6 crores of smart meters were deployed. There are some tenders rolled out where some of the states are going to deploy advanced distribution management system. There are, at state level, they have an asset management control center just to have more visibility and outage management, etc. But I think there's a long way to go there. I think when we talk about smart grid, we don't even know how to manage, how to use the big data which is coming out of the smart meters. So we need systems which deploy artificial intelligence and machine learning technologies. We need trial programs by government which could be run in certain states where you could see the use case, you could understand the benefit and reiterate in terms of how do you apply it in another utility. Because in India, the load pattern, it differs from north to south. From two cities, they have the loading pattern, the consumption pattern is very different. So one solution will not solve the problem. So that is why in order to frame a policy, in order to encourage DISCOMs to adapt to new technologies, I think some trial programs funded by government in this direction would be helpful. So yeah, that's all from my side. Thank you.
Yeah. Thank you, Mr. Vishwajeet Singh. So, although we do not have much of the time left, in fact, we have exceeded the time. So, if there is one question that we would like to have here, otherwise, yeah, please be specific with the question. Other questions, probably we can take it along the lunch.
I have a question for IISc. I wrote down the question, sorry. For IISc, C-DAC and Ministry of Electronics. I am myself Ajinkya Nikam. I have my own startup named Ambed Urja. I am working in the field of electricity theft detection. In the field of electricity theft detection, I did and I designed some hardware plus software which is based on Indian market, because I personally feel smart meters is a Western concept and it's not going to be helpful in India because our population density is different, Europe's problem is different, and we are just copy pasting the technology as it is. So I designed the meters for Indian context. I designed a system where I can detect the electricity theft between two poles, not on the transformer level. So I want to know how IISc, C-DAC and Ministry of Electronics can help me to implement this startup and project on the vast level.
You want to answer now or take it during the lunch time?
I mean, in the your question support for the startups. So under this NaMPET program, there is a scheme for the startups also. I mean, technical supports. So whatever your problem like smart meter indigenization and all things, I think it is under the NaMPET. So I think better, Renji sir, what kind of support we can provide it and how we can incorporate in that.
Yeah, regarding smart metering, it is a basic requirement, is basic technology, and then when it comes to the Indian condition testing as per the standards, the product development itself with anti-tampering and other protection requirements. So that is as per standards which is required. So when it comes to as a product, it requires the utility requirements and other things. So as a product when it comes. So if you have it is a complete requirement or a solution that is meter, then data acquisition, and then the other parts coming in the AMI architecture. When you implement, it is not a simple solution. Actually, it's a package of systems with the hardware, software, and other things which need to be implemented in a large scale. It is not in a small scale. It cannot do it. It has to be at a large scale. So here you have to associate with relevant entities in this field like AMI, SP service providers. And if you have a technology, then probably the NaMPET can discuss with what is the kind of the advancements or the specific technology that we will be having that can be integrated into the technology that we have done, or whether you can adopt the technology that the NaMPET has done into your system. So that way of a mutual discussion can be done, so that both the synergies can be, maybe you may be expert in, or you have activities in one area which we may be lacking. So that combined activity we have under NaMPET, that is startup promotion activities are there. So probably you can contact, and probably we can explore how effectively this can be taken forward for the mutual benefit. And we need a lot of technology supports in this one for the large scale deployment that is going on when it comes to for a sustainable solution for the next 10 to 20 years or so. So we can keep in contact.
Yeah, thank you.
Hello everyone, my name is Jugal Shadatpuri and I'm the founder of Bombay Power Co. We are manufacturers of EV charging systems, and my question actually would be to anyone, frankly, because I missed half of the session. So we are trying to integrate EV charging systems into a smart grid by way of V2G technologies, obviously. We are also exploring if electricity would be democratized for being procured by way of open access model. So when we're talking about centralized grids, when we're talking about decentralized grids, when we're talking about something like a prosumer, how do you feel that whether if open access model, that means power trading by way of something like an IEX, would that see the light of the day for the masses, or would it be decentralized grids for every small little community spread across the country?
You're asking a very interesting question. So I just wanted to understand what is your salary versus the pay that you are going to, I mean, the payment that you are going to do for your electricity bill.
My salary versus payment?
What you are going to pay for your electricity bill?
Going forward?
Even now, today.
Even now, residential probably I think the average cost is 10 rupees per unit or 11 rupees per unit.
I'm talking about your bill versus the salary that you have. This is essentially what is most important. The per capita consumption of the country is not even some percentage of the advanced countries that you have.
That is true.
All these concepts that you are talking about, in my opinion, are just borrowed simply and trying to impose, and which is not going to be a good aspect. Let's look at radically different and see what works for it.
Okay.
That's my take on it.
Right. So in your opinion, something like an open access model would not work for India. Are you suggesting that?
Open access at a level that you're talking about the bulk power grids, yes. I agree that there is a lot of feasibility. But at the consumer, coming
Not
to the
at retail
prosumer, talking about everybody to talk about it, it doesn't make any sense.
Follow.
Right? Yeah.
Right. Thank you very much. Thanks a lot, sir.
Yeah, thank you. So I would like to conclude this session finally with key takeaways, and I am sure that the entire house agrees with one key takeaway with which we can conclude that probably we are now at the anvil of UPI moment for utilities now for India, and the way in which our R&D organization like C-DAC, the premier academic institutes like IISc or VNIT or IITs, and the startups and the industries are working in India. Very soon we are going to have something like India Stack for utilities as well. So with this hope and the passionate belief that we would be very soon having much of the indigenous work happening in utility segment, I would like to conclude this session, and I thank esteemed chair of the session and all my panelists. And most importantly, the amazing audience that we had today, because it's much like 20 minutes past 2 p.m. and I could still see a lot of enthusiasm, and we'll carry this enthusiasm further towards the lunch hours, and you may probably be interacting with the other people. Because of the lack of the time, we could not take much of the questions, but we will definitely be interested in discussing with you what are your ideas, and all these panelists will be available post-lunch. So thank you very much, ISGF, as well as the session partner, C-DAC. Thank you very much.
Thank you, sir. First of all, I'd like to thank Tripta ma'am for